Can you mute your speakers?
Mine is muted right now. Let's make sure everyone else is just muted.
I think the problem's going to your speakers, though. Or is that coming through the projector?
I don't know. How do I turn up my speakers?
Function F10. How about now? Better. There we go. Much better. Okay. All right. This is going to go great.
Okay. You want to give an introduction, Steve?
I sure do. All right. Welcome, everyone, to another night of Pearl from Milwaukee. Tonight we have... Let me make sure I'm talking right. You guys can hear me? Okay. Get some echoes. This is going to be perfect. But sorry we're getting started late because the pizza's not here yet. We'll try not to stop presenting and go eat pizza. No promises, but tonight we are going to talk about databases. We have a special guest tonight, Phil Vaca. He is a Postgres expert. He's currently working for a little-known company. Just kidding, they're well-known. Enterprise DB. They're doing a great job of converting people from Oracle to Postgres. And so he gave a presentation a little while ago on some wonderful full-text searching that he's going to share with us tonight as well. So thanks so much, Phil, for coming on late notice to give this talk. What I'd like to do is, if things work out, some of the stuff he's going to talk about and the techniques, I'd like to show how to use DBIS class to implement some of these techniques. If that works out, we'll kind of give some demos later, but if not, you'll have a great time watching his presentation. So go ahead, Phil. Take it away. Thanks so much.
Cool. Thank you, Steve. This is the greatest screen I've ever seen. Look at that. Look at that. That is... Wow, I do not want to disturb that. That's really terrible. It's still going. It is going on into infinity. Wow. It's just turtles all the way down. Okay. Well, thank you, Steve, for inviting me to the talk tonight. Don't have a whole lot of Perl-specific content, and it's too bad for me because Perl's a great language, and I know people are excited to talk about it. I am here, however, today to talk about PostgreSQL, or Postgres Server, which is a topic near and dear to my heart. I work with Enterprise DB, or EDB. I'll give them their obligatory plug. Why not? You know, hey. Enterprise
They
DB.
paid you to write this presentation. So.
They did pay me to write it, so I may as well say something nice about them. They're a consulting company based out of Boston. They've got offices across the world, actually, and we're probably the largest exclusively Postgres-based consulting company out there. So if you're a small, a medium, or a large company, and you've got an open source database, whether it's Postgres or whether you're thinking of converting out of Oracle or Microsoft, and God, I don't know why anyone would want to, but other than not wanting to spend all that money. Then EDB are the people you want to talk to. We've got great consultants who will come in and help people plan out a migration.
Quick question. How much does Postgres cost?
Postgres is free. It is a completely free database. It is a free and open source. And it's not even free the way MySQL is free, but it's owned by Oracle, so everybody pretty much assumes it's not going to be free for much longer. It's actually free. It's a free foundation, and that foundation is endowed into perpetuity. The downside of Postgres is it's an exclusively open source community, so it does not have the marketing push that Oracle has to put behind MySQL. And yet, even so, MySQL is steadily losing market share, and Postgres is steadily gaining. There's also a bunch of other competitors in the middle there. Actually, Postgres is the #4 most popular database server, according to dbrankings.com. And that, in fact, you know, I just learned about that DB rankings thing, because I was lamenting, like, what do we need to do to get that trend upwards when I was at PG Open, and I found out that the DB ranking, which is an interesting page, it's a fun page to go to if you're ever bored. Nobody's sure it's super accurate, but it only concerns the word PostgreSQL, and it does not consider the word Postgres when it does its ranking searches for popularity, because the database is named PostgreSQL and not Postgres, so it doesn't. I'm like, well, if you're trying to gauge popularity of a database, that's probably, you know, people are still using that term to search it. There's a lot of name confusion, so. The words are interchangeable, by the way, if you've ever been curious, Postgres and PostgreSQL. This is the full and official name of the database. They talked about changing it once upon a time, but they decided it already had too much name, cache it, and they didn't want to. They went and did a list of all of the modules in Postgres proper that would have to be renamed, and they're like, wow, this would be like a major rewrite just to scrub the words SQL, PostgreSQL out of it. So all of that said, welcome to my topic today, which is searching text in a Postgres database. Do you ever have to go sifting through text? Like a lot of text, row after row, file after file. How will you ever find that one thing you need? Postgres can do this. You can't see the lettering, but that's what it says. It says Postgres can do this. It's spent a lot of time trying to get the JavaScript to make that show in red letters instead of dark gray letters, and ultimately said it can't be done. Can't be done. I bet Postgres could. How do we search text in Postgres? Well, let's talk about the basics. First of all, what is text in Postgres? Text is stored in the basic character types. The SQL standard defines two of them, character and character varying. Character is a fixed length field, varying is a varying length field. That is what the standard defines. Postgres, we have both of those types, but we also have the text type. And if you've used Postgres for any extent, you've probably seen the text type. You might be asking yourself, which one should I use? Should I use character? Should I use varying character? Should I use text? Just use text. Just use text in your Postgres databases. Some people think to themselves, well, what about fixed length characters? Isn't fixed length character better? Well, here's this addendum that was actually in the manual. Well, character N has performance advantages in some other database systems. There is no such advantage in PostgreSQL. In fact, character, fixed length character, is usually the slowest of the three because of the additional cost in storage. So if you have varying character, just use text. If you have fixed length character, probably just use text unless you really, really, really need to constrain it to exactly a specific length. One example might be phone numbers. So you had phone numbers in a database, and you know that they will always be 10 characters and 10 digits in length, and you're not storing this character. You're just storing it as, or I'm sorry, and you're not storing it as an integer. You're just storing the actual string, which you should. Phone numbers are not integers. You can't average them. So,
Could I take a real quick tangent and ask you a question about, step up here so you guys can hear me on that microphone, but is there a performance improvement if you did something like took a SHA-1 of all of your text and had a fixed length character string and you used that as like a primary key, and then when you did searches on a known value, instead of searching a variable character length string, you first took a SHA and then searched against that fixed character length?
That is almost exactly what text is doing behind the scenes.
Okay, interesting. I haven't, because what I want to do is just like run a proof of concept, like generate a whole bunch of data and just kind of test it out to see what kind of benchmarks I get, but I'm just curious if you know offhand.
Yeah, we actually did put that into effect in the Inspector X database. We took addresses, and we took the formula was first name in a fixed, or a first address line 1 in a fixed space, and address line 2, or we put a character in, I think address line 1, pipe, address line 2, pipe, city, state, zip, or pipe, city, pipe, state, pipe, zip, and took a SHA of that and used that as the actual primary key for the addresses table. And we did that in instead of storing it in a text field, we stored it in a can't think of the name of the data type. The data type that is actually raw binary. It's not bin. It's not blob. There's a I can't think of the name. It's not MD5, but it's like MD5. There's a fixed byte size. There's a byte R.
Oh, yeah.
We took the hash and we stored it in byte R, so it would be a fixed. Then we put an index on that byte table, and so any incoming address we'd hash it using that formula, and that would be a faster lookup.
Yeah.
What's that?
It's not called
byte A. I'm sorry, byte A, not byte R.
Gotcha.
Byte A. Thank you. Yeah. It's one of those underused data types. And speaking of underused data types, Postgres, in addition to having text, has a couple of weird ones that you probably won't see too often. Char in double quotes. That's not me adding quotes to be like, hey, char. No, no, that's actually a data type, and it is not char1. Char in double quotes is an internal system data type that it uses for one character representations in the system tables, so that it can have, you know, if you see the letter B in one of the system tables or something, that's not a single character char, that's this data type, and it's not the same one. You have to cast it if you want to use it. There is also a data type called name. Name is exactly text, except it is text that has been optimized to be used in the system catalogs and max out at, I think, 224 characters. And that's what they use for actual like relation names, index names, things like that. And we also have structured text, not just text in a blob, but text in some sort of format. There's an XML data type in there, and there's a JSON data type in there, but not the JSON B type. And anyone think, why? Do we know what the JSON B type is? JSON B is binary JSON. It's an actual compiled version of JSON. It was added into Postgres in 9.4. So in 9.2, I believe they added JSON as a type. In 9.3, they added support for using JavaScript to query JSON natively. So you have a V8 language you can add as an extension to Postgres. So you can have stored procedures written in JavaScript that query your JSON data. And then in 9.4, they added JSON B, which is actually a binary encoded. Right now, it's got some storage problems. The storage size of JSON B in some cases ends up being larger than the original JSON, but it is still faster to search. They're working now on trying to get, they haven't figured out why in the end, because it's also supposed to be compressible. So it's always supposed to be smaller, but some cases they found the JSON, if you run it through into the JSON B, it actually becomes larger on disk. And they're like, that's weird. Why should it do that? And it shouldn't. So, but nonetheless, it's a good type. And if you are web developers and you have a lot of JSON data, you might strongly consider just throwing it in JSON B and putting an index on it. What kind of index? Besides text types, there's also character encodings, but that's a whole different ball of wax. Let's just not talk about it today. You can have a different talk about character encodings and Unicode typesets and things like that, and people's heads will. It's just a boring topic. I'm sorry. I don't care how much people love text or rich text. The Unicode standard, trying to figure out the byte order mark and UTF-8 versus ISO whatever 18859 or whatever. Like, ugh, who cares? So let's talk about querying text. Well, we all know how to query text. We can use the like keyword or the like command. So, you know, where text like something. Postgres also had, because Postgres is a case-sensitive encoding, speaking of encodings, meaning that uppercase apple is not the same as lowercase apple in the text. It also has I-like for insensitive like, and all that does is behind the scenes do an upper, might be a lower, but I think it's an upper. Also has a really underused keyword which you can use called similar. So if instead of where something like, you can do where something similar, and similar supports a subset of the full regular expression syntax. It supports about 8 characters in regular expression that you can use to do small queries, but there's no real reason to do that because it also just natively supports regular expressions to query. Here's a beautiful, trim, elegant regular expression for, can anyone guess? Can anyone who's good at it look at that and say what it does? That's exactly right. This is for validating email addresses. So if you have huge blobs of text in there and you want to know whether or not there's an email address somewhere in there, you can do where the column is tilde and the capital E tells it that this is going to be a raw expression, not to do any character replacement rules. And there you have it. Who doesn't like regular expressions? Man. Idiots. Right. But these methods aren't always that good. First of all, you need to know the correct spelling of the thing you're looking for in advance. And you have to hope that it's spelled right in the database. Also, words with the same root don't match. So for example, the word democracy, if you're searching for it, will not match any text that has the word democracies. There's lots of words like that where the singular and plural have different spellings. And then you end up writing really crazy regular expression rules for words like that. But that's just a pain. Again, this is not the kind of coding we want to do. And it doesn't scale. So those indexes get Slower and slower. A standard B-tree index doesn't do much to help you with a text search. The standard index of Postgres. One second, I think I'm not going to say anything, but I dimmed Flux, which changes my color settings, for a whole hour, and it just ran out. Let's go back to this one. Presentation. It doesn't scale, so a standard presentation. So if you have 100 bytes of text and you search it, it'll be very fast. If you have 100 megs of text, it'll be very fast. If you have 100 gigs of text, it will be very slow. They will get slower and slower because if you use a like comparison, it has to go through every bit of the text to find out if any part of it is like the text. It's not what we want. We want better things. You might think, well, let's put a standard index. The standard index, if you just type create index in Postgres, is called a B-tree index. That's your typical index type. It starts with the first character furthest on the left, and it orders things in order, basically in alphabetical order or in character encoding order, left to right. But again, that only helps you if you're searching on the first character of text. If you're just trying to find something in the middle of the text, it can't do that. You can write an expression index. So people who really know their Postgres say, well, I know what you can do. Postgres, you don't just index the column, you can actually index an expression. So if I wanted to say, where like and a specific regular expression, that email regular expression, for example, you can write that expression and create an index. And Postgres will maintain that index. It will be slow to maintain, but it'll be fast to search. But that's only going to help you if you know the search that's going to be coming in. So your email search, all right, you know what those look like beforehand. But if you're just trying to get arbitrary user input that you search and alike, you'll never be able to come up with all the regular expressions in advance, and it's a fool's exercise to try. So how do you get around it? How do you get around all these limitations? Well, Postgres has two very important features that you can add in the extensions. One of those is called PG trigram or PG trigram. Everybody says trigram, but it's PG trigram. What does it do? It is an extension not for helping you find exact matches of words, but for finding word similarity. So how similar are two different arbitrary text strings? It divides each word in the string into 3 character segments. And those character segments start with 2 spaces on the left and 1 on the right. And I'll show you a visual in just a second so you can see what that looks like. And it ignores non-alphanumeric characters. So periods, exclamation points, dashes, Unicode, smiley faces, all that stuff is stripped out, and it only deals with numbers and letters. So here's what a trigram looks like. You can see I took the 2 words, I misspelled spelling, and the other word is spelling, and I put an exclamation point on the end. You can see that what it does is it starts furthest on the left, and it divides it up into 3 character chunks. Again, it assumes that every character has 2 spaces padded on the left. Why 2? I honestly don't know why 2 and not 1, but for a reason, Postgres people are smart, so they have a good reason. And you get new commands that you can use beside once you create this extension PGTRGM. That's all you need to do to be able to use these functions. Create extension. If you're on Postgres 9.1 or newer, the extension system was wildly revamped and became very, very simple to use. So it's literally that one statement. If you're running Postgres, type create extension PGTRGM, and you can get started using that. You get access to these functions. Some of them are like this, show TRGM. Really, the only thing that you can do with show TRGM is to do this kind of demonstration. Like if you're curious if you actually want to see how many trigrams things have in common or what the word looks like. But it's helpful. I mean, it's helpful for debugging. Similarity will tell you what is the percentage of those two. Out of all of the 3-letter blobs that it came up with, how many of them are the same between these 2 words? This says that 38% of them, 38.4% of those are similar. Distance is the opposite. You have a new character that you can use in your queries. Instead of using a similarity function, you can use the distance operator, which is the left brace with a dash in there, the left-right angle brackets with a dash between them. And that's just the inverse of similarity. Distance is 1 minus similarity. And then show, and it will tell you what is its similarity ranking. So if we want to say, are two words similar, you get a new operator in addition to the one that shows you the distance. You can say with the %, if you have if you're doing a text search and you have trigram installed, the % lets you return yes or no, whether one is similar to the other. So in the first statement is that first word. Remember we said our show let's go up, when we showed the limit here is 0.3. So we're saying by default, that's the default number Postgres comes with. Any word that is 30% or more similar, it would show up in your search if you've got a million lines or something, the words that are 30 more. But you can make it more strict if you want. You could make it 40%. So if we look, these two statements, the statement itself is identical. Case 1, this word mod this word or similar to this word with that operator, then true, else false. And then we increase the limit. We move the limit up from 30% to 40%. And of course, since we know that it's 38% similar, it doesn't show up anymore. So now it's false.
So is that returning null if it's below the limit? What is the return value if it's below the limit? It's not following
that. Let's just say instead of 2 text strings here, I had 1 text string and a column. I didn't know what was in that column, and I wanted to say, is this text string in that column somewhere? It would show the rows that meet that limit.
Yeah.
Yep. So if there's no rows, then yeah, it would return 0 rows.
Okay.
In this case, I'm putting it in a case statement so that I can use a true or false and just show would this be found or would this not be found.
Okay.
Yeah, good question. And some basic facts about PG trigram for getting around. If you create PG trigram, what do we need to know? It is not case sensitive. It is not interested in case sensitive search. By default, you don't have to install anything. So it doesn't matter if your column type is text or CI text. Word order does not matter, but accents do. Let's look at first string is all caps I am Sam versus camel cased Sam I am. It says that those two are 100% the same because it doesn't care about word order and it doesn't care about case. But are those two the same, the letter E and the letter E with an accent, whatever that is, accent grave, I think? No, they're not the same character. It knows they're not the same character. It doesn't treat them the same.
That's interesting because what I've noticed now is that with the Spanish language, is that some people are skipping the accent marks, which are very important as part of grammar, and just writing. So if it's an email, if it's Twitter, they're just writing, and then you have to think about it as to where the accent mark should be.
I bet that would be very confusing for.
Yeah, but then the thing is, it's still, to me, it should be similar.
Yeah, and there is. So this is out of the box behavior, and if we weren't skipping over the part on encodings, because character encodings are really, really important. You can make the encoding actually treat accented characters as the same, but it's more low level than it's worth getting into at the moment. But if you actually did have a lot of character data that came from a lot of different sources, in the United States, that's easy to find. And obviously, there's plenty of people who speak Spanish or type other languages, not to mention all the other immigrant populations we have. You might see various spellings and character encodings and things like that. Then you have to make that choice right away. Are you interested in keeping these two things separate, or do you want them to be treated the same? And if you do, you have to do some special setup at the very, very beginning. It's really hard to migrate after you've already got the data. You really need to start up front and say, this is how this is the encoding style my database is. False alarm?
I was just checking because I don't know if you noticed that I get up here. So no sign of pizza yet.
How does it scale? We already said that scaling regular old text columns is bad. It doesn't, the more there is, the slower your computer gets. Don't know if any of you are fans of the old television show The Prisoner, but I am. Got a few references here. Hold on, are we talking about indexing? Yeah, okay. How do you scale a lot of text with indexes? If you have installed the PG trigram extension, you will also be able to see massive speed increases for traditional like and I like queries without any other effort on your part, simply by indexing those columns with a gin or gist operator. So we get these two new index types. And any type of query, not just these fancy-dancy queries that have the operators, the similarity operators, but any kind of query you do with text like or text I like will show a benefit. These indexes will not aid, ironically enough, in a total equality search. So if you're doing, like if you know that all 10 characters of your phone number and you want to find the other match that matches 10 characters, you can't use a GIN or GIST index or it won't give you any advantage. It'll be just like doing a heap scan. But you can add a B tree index. Now most of the time with text data, you don't know the fixed length. You might, for example, with a city, if you've got a list of cities and states, well, you probably know the spelling coming in, so you should use a B tree index and maybe a GIN index if you want to do partial searching, which we'll get to.
So you do like longest prefix matches on phone number a lot, and you use some funky extension, there's like an @ sign.
Yeah, then that would be the right way to go. And if you're using that operator, then yes, you're probably using a GIN or GIST behind the scenes. Semantically the same. That those operators are used to do searches against those types of columns. So let's talk about these fancy new index types. The first is GIST, the generalized search tree. It's what we call a lossy index, because basically what it does is create a hash, but it knows that hash isn't perfect. So it first of all gets all the results that were met by the hash, and then it has to go to disk to see if those hashes actually represented real hits or if they were false hits based on the hash. So any hit that it does, it has to do 2 steps. It can't just go to the index and do an index-only scan. The generalized inverted index, which is a whole different indexing algorithm, is not a lossy algorithm, and it's much faster than GIST. It's probably 2 to 3 times faster in most circumstances. That's just a rule of thumb. You're always going to have to test yourself to find out is it faster for you, but GIN is much faster than GIST. It is not a lossy thing, which means that if you do a search, the search only has to go to the index to return data. It never has to hit the raw tuples on disk, unless you're getting more of the row than just that text. But however, GIN takes longer to build, more than 3 times longer to build. It will take much longer to update. So if you have a text table that is frequently hit, it will be much longer. Your updates will slow down, probably to a point where you'll notice it if it's a busy production system. And it's larger on disk, so space is a concern for you. And it's not as much of a concern, but it's still a concern. GIN is larger on disk than GIST. And that's what PG trigram gives you. It gives you those 2 new index types. And if you use those indexes to index columns, you'll get faster like and I like searches. You'll also get those fancy similarity operators. The other thing that Postgres offers you for searching text when you're not interested in similarity, but you're actually interested in finding semantic content in the data. So when we're trying to find democracy and democracies or elephant and elephants, things like that, you can do similarity searches and those will come back, but full text search is probably what you want to do. So for example, if you're doing a research paper and you have tons and tons of text data that you're searching through and you want to find about the relevance of 2 terms near each other, how often does the word patriotic and democracy show up together versus subversive and democracy or something like that. You couldn't do that with a trigram operator, and you couldn't do that with a like. You could do it with a like search, but you don't want to, because for all the same reasons we just talked about. You want to do that in an actual search of catalog. You want to find out the frequency of those words and how often those words appear together. What that means is a full text catalog isn't actually the literal text representation. The literal text is the literal text. So if you have a text column in that data type, text or varchar or char, it's literally storing the actual characters left to right that we expect to see. So like those letters, FULL space TEXT will be stored. The PG, the full text catalog, does not actually store the text. In fact, it's not even the text type. Instead, we get a brand new type called TS vector. TS vector has a bunch of fancy rules. The first thing it does is it eliminates case. Then it removes what it calls stop words. Stop words are small words that are not semantically relevant. It considers words, little helper words, and, or, nor, for, should, not, were, he, him, was. And there's a list of hundreds of them. Postgres committee does not come up with these words. It's not a Postgres specific thing. There are natural language researchers out there, like Caltech, and 1 or 2 of the other big research institutions that go out there and publish these catalogs, and those catalogs are brought in at the time when they're compiling the source for Postgres. So if you're using the full text extension, you've got whatever the most recent catalog was that was published by other people who do research in text searching. And it's difficult to go build your own, it's not impossible, but if you start with the English dictionary, you know, the full text dictionary that it has, it's not super easy to go. And if you say, well, I want all the stop words removed except the word him. I want him and her in there because I'm doing a gender studies study and I want to find out whether pronouns are outdated or something like that. You know, you would actually have to go in and hack the system to do that. Then what it does is it replaces the actual word itself with a stem for the word. And again, these stems or phonemes that it creates, these are out of a gigantic dictionary that these researchers have come up with. So the word elephant, you don't store the whole word elephant, you store E-L-E-F, which means other words like elephants or elephantine, they would also fit with E-L-E-F. And all instances of those words will be replaced in your full text catalog. And lastly, oh, I'm sorry, these columns can and should be indexed with gin or gist. Now, either of those two index types can be used on these tables. Same rules will apply. Gin is slower to build, but faster to search. Gist is very fast to search, but not as fast as gin because, again, it requires a heap hit no matter what. And it will always be faster to build and update. Full text does much, much more. I thought there was one more important thing to say. Oh, in the word stems, I missed it saying, it also replaces what I think is perhaps the most important thing and probably should have been its own bullet, and that way I wouldn't have missed it. It replaces synonyms. So it might say the word prairie and the word field are synonyms for each other, and you don't know which one's going to be in the actual full text catalog. So if you search for the word field, you might get hits back in a full text catalog that included the word prairie and not the word field anywhere in it. You'd be saying to yourself, why? Why did it do that? But that's because what the expected behavior is this same consortium that does the research of these language types. And they don't just do it for US spoken English. They do spoken English and other dialects, British English. Do Canadians count? I don't know. They're so easy to pick on. I don't know, something. But there are also there's a German phoneme catalog. There's a Spanish phoneme catalog. There's a French phoneme catalog. So you can get those catalogs when you're installing your database or when you're installing your full text catalogs and tell it, instead of create as, its default is create as English, you can tell it create as French, create as German. And it will do these same kinds of words, but these same kinds of replacements, but with German. So I don't know what a good root word for you know, I don't know. I've looked at German and they just add words longer, right? So I don't know what the phonemes would look like there, but I'd imagine there's got to be some kind of rules to it. Full text can do much, much more than just that. You can create custom rankings with weights, which means you can say that the word, when we're talking about democracy, we can say the word democracy is worth a certain score, but the word democracy is worth more if it has the word patriotism next to it. That will increase the score and the relevancy when you search for things. You can weight certain words as more important than other words. You can, as I was saying, you can use other natural languages. You don't need just US English. You can just get the other languages dictionary. If you're doing PG full text search with TS Vector, you can just go to the web page. It'll show you the link to all the other language catalogs if you happen to have a big natural language set. And you also get these operators. So just like Dan noticed using just index, the @ sign with the bracket going left or right, the bracket, those are the operators for saying whether or not a column contains text. You can also combine search terms. So just like I said, if you want multiple occurrences of different words in there, you could. So let's look at some actual performance. Let's see how you would use these things. How does PG Turgum scale? Let's start out by creating a small table. We'll just make it a 1-column table with some names. I created a table. How was that database? Man, I was looking right at it. Anyway, I created I went on the internet. I downloaded the 1,000 most common surnames. So I got a list of 1,000 names. 1,000 isn't a whole lot. I figured we should put more text in there. So I took the 26 letters and we cross-joined it 2 times. So instead of having 1,000 entries, we have 1,000 times 26 times 26. Now we've got 676,000 rows. This is just on my MacBook Pro too. So I'm not claiming that these are, when I show you the performance numbers here, I'm not claiming that this is the kind of performance you get on your own database server. This is just what I got in the virtual machine on my Mac. So. Created an index on there. The first thing we'd normally do if you got a whole bunch of names, you know, your typical thinking process is let's put a standard unique index on there. And that's going to be the best possible index you can get. It took it about 10 seconds to create the index. So first of all, let's just try and do a search. To me, account star, using that case-insensitive operator, the % that we can use, but no index on the table. We're just using the operator. How fast can it scan it? Pretty fast, 658 milliseconds, 667,000 rows, 676,000 rows. Yeah, you know, that's quick. All right, I don't know how that compares, but all right. What about if we do no index, but we do an insensitive like search? Case where surname I like Mill instead of I know where the word is Miller. It'll show me the word, just all the words that begin with Mill, M-I-M-L. 1,300, and it did it faster. I actually did that faster than using the case-insensitive operator. Now what happens if we put indexes on there? So let's put an actual gist index. For the purposes of this demo, I didn't ever add gin indexes. So if you're waiting to see, well, oh, gin, how fast does that get it? You know, yeah, it just took too long on my MacBook trying to get something to create. So I just did gist on a bunch. And what the lesson there was is that it does take substantially longer to create, and I believe it. So now let's create it. Remember, we were at 676 milliseconds, 10 times improvement. 64 milliseconds to do the same search. And I like search. Now again, remember, this would mean that the user has to do nothing different. All we have done is put that index on the column. 17 milliseconds. We started out at 676. Heck of an improvement out of just one index type.
Wait, so the trigram helps with just generic partial matching?
Mm-hmm. Yep.
When it does the search, does it do something to the mill % to convert it into something that can compare against the trigram? Like, is that built into what the iLike is doing? Or? Because I'm trying to understand how it makes use of the trigram index.
Well, the trigram itself isn't the index. It's gin or gist that's the index.
Oh, okay.
But by installing the trigram extension, you have access to those two index types. Okay, so you could add one or the other of those indexes.
Gotcha, thanks.
So let's just see it with more numbers. Okay, so let's do one more cross join on there, and now you got 14 million rows. 140 million rows, whatever. It's 10 times more. Took 123 seconds to create that table. 2 whole minutes of my life I spent watching it do that. Add an analyze full on it, and no results. What the heck? Where'd they go? We're going to analyze on it, and it's gone. Well, you'll just have to take my word for it. That it's probably in the, I don't know, did it get commented out in my code? That the results are in fact, and as opposed to being exponentially worse, as you would get with which is the demonstration when you do like and I like with no index. It's not, we're 20 times larger, 200, whatever, however many times larger, but the search isn't that same amount slower. It's much slower than that. So if you have 10 times the amount of text to search, it's slower than 10 times as much to search it. And the more text you add, the slower it will get in an exponential fashion. However, PG, trigram, I like, and mod searches, those are linearly proportional to the amount of text. So having 100 times as much text takes about 100 times as much time, maybe less. In fact, in many cases less. And having millions of times more text where we were, it actually still came back in a relatively good amount of time, like 3-4 seconds. And again, that was on my MacBook Pro. I wish I had the slide to show you because just me saying like, come on guys, I'm telling you it's that fast. But we saw that first result set, and I'm really confused why the second one isn't in there. So I'll have to find it. I'll send it out to the group. I'll post that when I find that slide. I'll post it up for you guys on ProMonitor so we can see how fast is 140 million rows with a GIST index. What about full text search? I created a table. I went out there and created a database. Took all the content in Wikipedia and downloaded it because it fits in about 30 gigs. And I started importing it into my database. I just created a very simple table called pages. And pages database just had the title, the ID, and the actual content, the text of the content. And in case I'm not going to give it away here, I also created a TS vector column of the content. So let's just real quick to show you like what a row of that looks like. So I don't know what I just got, but we got, and I only loaded about half of Wikipedia because I got bored doing it the night that I was making this presentation. It took a while, but so I loaded about 15 gigs of data, of text data in these little rows. This is a nice for the May 21st predicted date of the rapture in 2011 end times prediction. So this is the actual article on that in Wikipedia. Here's the markdown for it. And then at the bottom here, this big long thing of words with numbers is words in their frequency in this text blob up here. So in that argument, in that particular argument, in that particular article, thank you. And a lot of it's being truncated off on the side because the words go off on the side, but we can see the word kingdom was used 149 times. The word begin was used 154 times. Many of these words, they're so abstract for us we can't see, but here's one where we can really see the truncating of the word. So this could have been the words earlier or the words earliest, but it gets truncated to E-A-R-L-I. Which is interesting because that means the word early would not match. But it will store in Unicode, however much, there's no fixed limit in Postgres. So you can just keep adding it up to the limits of your actual physical hardware. It will get predictably slower and longer to search unless you do strategies like this, adding indexes on it. And those indexes take up space. So having the amount of text that I had before I indexed it was about 20 gigs. Once I indexed it with full text, it went up to be about 35 gigs. So the physical amount of text and the physical amount of represented space here, it takes up a lot of space to create these indexes. But there's no actual limit. So some of these, I did a stat on the length of the number of characters in all of these Wikipedia pages, and some of them are, 40,000, 40 million characters, and there was, no limit. It doesn't truncate. There's no arbitrary length limit. Postgres has a mechanism behind the scenes called, they call it TOAST, and it's, the acronym stands for something. It's off-row storage, taken off. What does Postgres TOAST stand for?
The oversized attribute storage technique.
Thank you. Yeah, and what that does is if it doesn't think that the length of text is going to fit on the actual row, it creates a whole separate table out there. Hey, there's our pizza guy. Anyway, so if it thinks it's going to go longer, it basically has an overthrow table, an overflow table, or an overthrow table, I guess, that'll throw all the extra stuff in. Let's just pick one more. Let's see a different article. Same one. Less than that. Totally different article. This looks like a good one. What we get. Baby topic. Oh, I went too far. Independence Day for Trinidad and Tobago. Holidays and observances. This must be observances of Orthodox holidays. That would be a pretty big Wikipedia article. And we can see that in addition to indexing the actual text words, it's also indexing characters about the words. I think I've only got one slide left, so if we're gonna eat pizza in a second, we can do that. But anyway, that's what the table behind the scenes looked like. I took the actual full text and then I created a second column on it and made a TS vector, which is that full text catalog we were talking about. I did a counter where the pages where the word elephant appeared. You can see that I put the word elephant since I'm interested in the word elephant, but I don't know what the phoneme is beforehand. I don't know if it's E-L-E-P-H or if it's E-L-E-P-H-A or whatever it might be because I'm not an international linguistics expert. So you use this function to TS query, which takes your search term and tokenizes it for the full text searcher. And we say where our vector column, we get another fancy new operator, we get the double @ sign. So essentially what this is saying is show me the number of pages that are like elephant. I found 8,700 of them in 22 seconds. It doesn't sound super great, but let's compare that to how much I could do comparing that raw text. I took 1/3 of the amount of data because I actually imported I had to break the Wikipedia page. There was so much text data that I couldn't just import it all in one chunk into my database. I broke it up into 3 text files. So I took one of those 3 text files and I said, well, how fast can Linux grep it? It's the same MacBook. It's got the same amount of memory. How fast can it grep it? Grep's a pretty cool utility. It's pretty quick. So I went and grepped for the word elephant, which again would not find, well, it would probably find elephants and elephantine, but other, if I had searched for democracy, it wouldn't find democracies or something like that. How many words did it find? It does not find as many hits as the first one did. It only finds 3,000, but again, we're only looking at the catalog. But instead of taking 22 milliseconds to search 20 gigs of data, this took 1.5 minutes to search 6 gigs of data. So full text search, huge order of magnitude faster than other text searching ways. I originally gave this a Postgres open, and so I should have changed that so it said, thank you, Perl mongers. If you're interested in following me online, I tweet a lot at Phil Vaca, and I tweet a lot about Python and Postgres and programming, data science, all kinds of stuff, and also things that really grind my gears. So you can find me on Google+, or you can follow my blog at 6for2.com. If you're curious what I was using that does all these cool text effects, they're all built in. This is all just a JavaScript framework that I found, and it's called Reveal.js. Continue.
Is it time for questions?
Yes, absolutely. Unless people want to get pizza while they're asking questions.
Is there any same way to use trigrams over several tables?
Over which tables?
Several tables.
Sure. You can put a trigram index on more than one column, and it will, in just the same way that you can use a B-tree index and index 2 columns, you can index 2 columns with trigram. And it will create essentially a behind-the-scenes like search for you. I would be really interested in setting up a demo to see, is 4 columns 4 times slower, or is it more than 4? Is it exponentially slower? I don't know. But you could. But the syntax, there's nothing about the syntax that prevents you from doing that.
How would I run to, or maybe with mixing multiple columns, if you're using the trigram search, if a user is being able to expect, let's say you're mixing less historic chunked out trigram, index it all together. If you say search for the house name, you won't actually get a match, or the house number, sorry, you won't actually get a match because there's so much text in the index that it just isn't.
That's a good question. I mean, one thing, so remember, trigram will show you how similar 2 strings are. So if you've concatenated a really long string that begins with the house number 2707, there could be millions of those hits that have that fragment somewhere in it. Let's see, how does it compare similarity between a short word and a long word? So if you have a short word, it knows that at least that much of the word is an exact match with this exact word because it's taking out all the special characters. But it must be doing the math to see how similar it is to the whole big long statement. So if you're just doing a trigram search, it's very possible that just the house number is not similar enough to the whole word, which would mean you'd probably want to break it up into small, like, you'd want to know what they're searching beforehand and probe just that column. If you took your addresses and broke them up so that the house number is one column behind the scenes somewhere or something, then you would get all the house numbers that are like that one that you're searching for. Same thing with cities, states, zips, stuff like that.
So we actually implemented a feature in LibRx using trigram and such. And in my practice, I found since we were across so many different tables that trigram wasn't particularly useful since there's so much text. Full text was too slow because it's not that much text. And it's hard to index since it's across different tables. And so we ended up actually using insensitive like and trigram on individual fields. Trigram where things can be misspelled, such as something. There's one way around using some kind of field.
Yeah. So if I were going to do something like that, where you want to have like a universal search for where as soon as somebody starts typing their address, I mean, I would try and find a way in the UI to limit them down to at least the state if you knew it beforehand, because it's going to cut your text catalog. You can create. There's actually an extension out there called btree gist, where you can create, like, let's just say you knew the state but you didn't know what the house number was going to be. So what you'd want to do is where state equals WI and address like 1, 2, 3, 4. You can use the extension btree gist to create a composite index that does one column btree and the other column gist. So if you have a very selective thing like states, where there's only 50 of them, and then a highly widely scattered thing like the house numbers, you could create composite indexes on each of those pairs so that you could get them to at least narrow it down, and then your gist search would at least be, then your I-like search, your traditional I-like without doing similarity, would get all of the speed improvements of the gist index, and you'd be narrowing the criteria that they're searching on by a huge magnitude. So you might see some performance increases there. But you'd need to pool everything. Like what you need is a centralized address table somewhere. That would be the right place to search. Or two, I mean, if you want to go into like how do we build address validating systems, in my opinion, you would use it. So somewhere out there are people who've gone through and have had big chunks of property data they needed to like normalize so that they could determine whether they had duplicate addresses mistyped and all the other things that go along with address data. So you have your final source of truth table, your actual clean addresses table, where there should be one and only one row for a unique property. However you define that property. Maybe you define it as the actual, like, the building. This is Google defines it as the building. So even if it's like 100-unit building, it just throws away unit numbers and says, here's the latitude and longitude of the center of this building, and I'm done. As a property person, like if you have, you might have to reinsure condos or something like that. Condos you can have 2 of them in the same building or 20 of them in the same building. They're not the same property, so your single source of truth table has to go down to whatever granularity you want. Does it go down to the actual residence? In the US, there's 120 million residences, which is why, well, anyway, there's 120 million residences, so if you've got a property database with even 30 million of them, you're doing pretty good. You've got a huge representative sum of data out there. You need a second table for the actual scoring of those addresses. You ran it through Google. You need the date you ran it through Google and the tokenization that it did, the whatever scoring and confidence it came back and said, when you gave me a dirty address, here's what I came back with. so that you can get it, because you might not use Google services again. You might use Yahoo services next time, or you might go out and buy your own mapping company or whatever. And be like, now I'm going to run it through my own proprietary scoring algorithm. Or maybe you have satellite data or something like that. You know, you have people out there with, you know, whatever rods that they hold up in the sky, and the satellites tell you, nope, I know the latitude and longitude that this is because somebody went out and walked it with a device. You know, so you want to be able to rescore addresses, so you can have multiple results for the same true address, even if they represent the same pure property. And then you need a third table, which is your actual, I probably should have started with the big one, the ugly one, the raw data table, which is whatever the user sent you that you turned into the clean address. So you want the raw, so you would really want 3 tables, and you would want to start probing when the user types something. You would want to probe the raw table and see how many rows come back in the raw table that match it, and use that to look up in your pure table the number of unique hits that your pure table gets. You can bypass that middle table. You can throw that middle table away that does the scoring. It's just really helpful if you ever have to rescore all your property data. But you definitely need a raw data table and a clean data table. And then the question becomes, do you trust the user enough to be searching the clean table, or do you not trust the user enough that you let them search the raw table and you use those results to return the clean hits on what you think they meant to type? And both of those tables I would probably do as individual, like address line 1 is a column, address line 2 is a column, address line 3 is a column, city, state, zip. Probably have your table structured such that house number is actually a tokenized, like you'll tokenize it out, get the house number, the cardinal direction. And then I would also have a column that is the full text search of the whole, of all of those columns. Like I'd probably put a view on top of it that is like column 1 pipe, column 2 pipe, like just like I was saying before for the hashes. Probably do something like that and put a full text index on that one. So I'd probably use just indexes on the first columns and a TS vector summation of all of those rows, or of all of those columns as one, and see how it works. And I would try and combine it with, like I say, use btregist, so that if you have a user coming in, you make them go through a drop down if you can. You might not be able to. Maybe you need to divide it up into nation regions, you know, Pacific Northwest and Southeast and whatever. Because then you can get them to put where region equals Northeast and address like 1404, whatever, you know, please.
Something like that. Some business people might have, oh, we need a search function. We need a search function. And we have it searching multiple different types of data, such as names, numbers, and multi-address.
They can search any of those things from the same little universal search box. Yep. Wow, that's fun. Then you do have to use it. Then I would probably just create a view that links the property with the known customers who have been to that property, or the known property holders. So I'd have a pure properties table, and I'd have a pure owners table, and somewhere I'd have a third table that is just the IDs, and then I'd build a view and index the view. I'd build a view of the text columns all blown out into one big long text column. And it would take a lot of storage space, but it will be relatively slow to update, because you don't get as many properties in as you get properties being looked up a second time or third time or fifth time, or, you know, I don't know how many times in your system the same property gets looked up, but plenty, right? Even in the same transaction, you know, you only enter that text data once. So I might go so far as to waste all the space and then put a GIN index on it, and see how fast it gets. You want to make sure, one thing that I didn't really talk on here much, to get the most out of your indexes, you want to make sure your system has enough memory that it can fit the index in memory, if it's a commonly used one. So one thing you can do is you can, I talked with Steve about PG pre-warm from once before. They're getting better at giving extensions where you can say, here's a table and I know I need this table in memory, or here's a relation and I know I need this relation in memory. So load it in, and then it'll keep it in memory as much as it can. You would want to see what the physical side, like, so if you have a full text, and I know I happen to know what StreetLinks does, so I would want to make sure that you have enough memory to load whatever physical size that GIN index turns out to be on your cross table between names and properties. And it will blow out to be huge. It'll be a pretty big table. But that's how much memory you need to start with. And then you also need the working set of memory available to handle the rest of like Blender X transactions. Because to get the most out of that index, you want it in memory as much as possible.
I compromise it on my Google search, and you type in a full address, it might not work because it's searching in the original column, so it's chunked. Over to support columns. Some
Come on. I want the world. I want the world.
Search on names and
There's food over there.
around.
Thanks, Phil.
Yeah, thanks so much, Phil.
Good stuff.
Maybe we'll cut it off here because food's here, and then if we want to stick around for some demonstrations of using TBS class to use some of this, I don't know if it's going to be worthwhile broadcasting. So we're going to end the on-air hangout here. So thanks again, Phil, for coming and doing your presentation last minute. Yeah. So, all right. Peace out. See you guys next time.